Okay, from now on I will switch to English since the exam will be in the language, so things should be easier, more comfortable. Having in mind that the main goal is passing the exam, so I should be acquainted with the terminology in English, etc. So let's start. So last time we left here talking about the joint distribution. Well, this is the marginal, the definition of the marginal distribution of a random variable, and so in the previous times I just gave an outline of the main topics of the course, and I started with some definitions. Well, we talked about the properties of a probability measure, we gave the definition of a random variable, the distribution of a random variable, the joint distribution, the marginal distribution. We tried in some way to give some additional remarks, and that's it. I was not very successful in the way I exposed the material, but as anything, it just takes practice. I will try to improve on that aspect, but if I don't start, I will never get better, so let's keep going. And as I said in the other video, the main purpose of all these videos is not actually to teach the material, even if that would be very nice, but the main goal is simply drilling a lot of theory and exercises. I mean, it's basically me sharing how I'm trying to study now. I tried almost any kind of approach, but this is the only way I have left. And well, let's go. So we left on marginal distributions, and let's start to talk about independence. Okay. So let's start with the definition of independence between two random variables. So given x and y, taking values in the measurable spaces E with the sigma algebra on E, and F, well, capital F with the sigma algebra on it, which we can call calligraphic F or script F, with mu and nu. This is a nu. No. Well, no. Their distributions. We say that they are independent if the probability of the joint distribution x and y factorizes into the product of the marginal distributions. If I remember well, it should be something like this: x belongs to A, y belongs to B, and if we have that this corresponds to the probability of A times the probability of B, well, x in A and y in B, for any A in script E and B in script F, well, then we say they are independent. Now, this was the case for n equal to 2. Let's say n equal to random variables. When we have n, well, n equal to n, let's say, when we have n random variables, so consider x1, xn a collection of random variables defined on this kind of measurable spaces. So, well, taking values on these measurable spaces for each I, for each xi, then we say they form an independency if the, well, okay, if the yeah, if the distribution of this random vector corresponds to the product of the individual distributions, so mu1 dot 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 mu n. So in this case, for each I from 1 to n, which is basically the same as above with more variables. So, well, this for example was mu1, this mu2. We can go on adding more random variables. Now, I actually think I'm explaining things better in English, or that might be just an illusion. So now we talk about an independent, well, a collection of infinite random variables which is independent. So infinite random variables. So given an infinite collection x1, x2, and so on, random variables, each one having a distribution as before, we say they form an independency again. So I don't know why it's, I mean, I don't find it very nice to have the same name for both finite and infinite case. Dependency. If any finite subcollection of it is an independency, meaning that any finite vector of random variables, if the joint distribution of each vector of random variables selected from this infinite collection is, well, an independency, meaning that distribution factorizes into the product of the individual distributions. More formally, nothing. This is just, even the definition I brought here on the notes is simply plain words. And what I have written here is let xn, well, this is an alternative notation that is used here in the written notes. So let xn be an infinite collection of random variables. It is said to be an independency if every finite subcollection of it is an independency. In the sense above. Question: why do we restrict to a finite subcollection? This has important implications, but I don't know really how to explain it well. And I actually find it quite difficult to imagine an infinite collection of random variables. I mean, infinity is quite mind-blowing, say. Okay, so we define the different types of independence and independencies, meaning that the joint distribution of, so the probability that x gets some value and y gets some value, they just depend on the individual laws that govern these random variables. There is no link between them. So the fact that today rains is maybe independent from the fact that I throw a dice and it gives 2. In this sense. So the proper let's read this note that I have here. To properly define a stochastic process, we first have to look at how infinite product spaces are constructed. So, infinite product spaces are the tool that we use to describe or model stochastic processes. This is an important sentence. And well, I will just give the notation infinite product spaces notation. Okay, the notation that we use to define a product space, and I will try to explain what a product space is that, okay, we have this big cross, big O times X, well, it's not bold, it's simply like this, over T in capital T of the sets of the, well, yes, the sets and the product sigma algebra of the sigma algebras, which we denote in this way. So we denote a product space in this way, or alternatively as the product of the spaces the product of the measurable spaces. So this is the product space, this is the product of the measurable spaces, and they coincide. And we also write it more concisely in this way: E superscript T, curly E superscript T, or just the most synthetic, not synthetic, the most how to say it, the most atomic or brief version to write it is this one. So what is a product space? We have different, let's say we have different random variables, and in particular let's focus on this case because in general when we consider stochastic processes we have an infinite collection. We want to consider infinite collections of random variables, and so to describe the law of this collection, this infinite collection, we want the joint distribution in order to describe the entire process. And to do that, we construct the product space. So the product space is nothing but the product of the measurable spaces of all the random variables composing the collection or the process. I think things are going much better than last time. So now let's define a stochastic process, which is one of the most important ideas we have to get acquainted with. So basically, let E, consider E script. I would like to write better, but I also have to be quick. So consider this measurable space. Well, in particular, I think that these two notations are used in when all the sets are the same for each random variable, but I'm not sure. Anyway, consider this measurable space, and then in an arbitrary index set, which we call capital T, and can be countable or uncountable. Now let xt be a random variable taking values this space here. Then the collection of all these random variables with t belonging to the index set is called stochastic process. So, in other words, a stochastic process is simply a collection of random variables. What is a collection of random variables? I have one random variable, I have another one random variable, I have another random variable. It's basically a set of random variables which is ordered in some way. So let's say, for example, that I consider as random variable the throw of a dice at each hour in the day. The first random variable composing the process is the first dice, the second one the second dice, etc. And all these collection of random variables, so this vector of random variables, if you want, is called the stochastic process. And one important remark connecting these two things is the fact that we can actually consider a stochastic process as an individual random variable taking values in the product space. And this is why we construct things in this way. I think it makes sense. So, with this said, well, here I tried to write down some clarification which doesn't make a lot of sense. And let's make some examples of random variables, which actually I don't know why in the course we list an example of random variables at this point. It would be more clear to do it when we talk actually about random variables. So, examples of random variables. Che brutto. Mamma mia, 3 Let's make a beautiful R. Oh, che bello. Random variables. Okay, so the first one is the Poisson. The Poisson. So the distribution of the Poisson random variable is this one. The distribution mu of A. I don't actually know really well how to interpret this. I mean, it is a measure and it acts on a set, but the link between the word distribution and this notation, I would like to find a better explanation for this. Anyway, the distribution, the Poisson distribution is the following one. It's the sum for the numbers in the set A. I'm bad with formulas. Of the exponential of something over the factorial a to the minus n over n factorial, maybe. And there was one piece missing. Well, here it's the note, it's written like this. Okay. Where this thing more explicitly is the density, the Poisson density. That is okay, e to the minus c to the n, yes, over n factorial. I should write this like 100 times in order to remember it. I don't know why, but it takes a lot of effort for me to remember this. So this was the sum of e to the minus c, c to the n, and factorial. We then in the natural numbers, and see which is a positive constant. Okay, and this thing we can actually see it like the sum of the Dirac measures. Delta n of A, correct. Probability that x takes value n. And this thing is it's 0 I never forget this. I never remember this. When n does not belong to A and 1 when n belongs to A. And the analogy with the indicator function, let's try to understand this. Let's make this in this way. This 0 when x does not belong to H, and 1 x belongs to H. So here we act in this way and here we act in this way. What is the interpretation and the link between these two? This is a function of a point which depends on the set. And this is a function of a set which depends on a point. But in either case, we have the fact that it's basically the same, since we have the point and then the set. The point and then the set. Well, anyway, this thing here is the Poisson distribution. So, a distribution okay, so we have to clarify some things. What is the link between the probability measure, the random variable, and its distribution? Which we can find here, here, and here. I don't know. Okay, let's move on. Let's try to speed up things a little bit. Now let's talk about the exponential. The exponential distribution, which is a continuous one this time. This was discrete, so we have values like, I don't know, 1, 2, 3, so on, since we have natural numbers, and here we denote it in this way, mu dx, mu dx, in differential form. And I don't know really why Sinlar's book uses this notation. I mean, this is the measure, and we just write this to remember that we are doing things with respect to the variable x in some way. So this I should know, this is the exponential of minus c exponential of minus cx dx, where the x is the Lebesgue measure. In which sense? I don't know. Simply So how can we explain this formula? Well, this is the Lebesgue measure, and this is the density, and this is the distribution. Why the Lebesgue measure is denoted in this way, or why? I mean, it's the natural way of interpreting integrals, maybe? Okay, well, in any case, we have that c is a positive constant and x is a positive real number. Now, the gamma. This is a bit more complicated and depends on the gamma function, which I never remember. The distribution of the gamma function is the following. Well, let's write it anyway. And I never remember this. I don't know how many times I will have to keep repeating these formulas. And as I said, the purpose is to understand, get acquainted, and also memorize in some way. Like, commit all this stuff to memory. And to commit this stuff to memory, it requires repetition. So we have to repeat and rewrite them many ways, and many times. So the gamma distribution is the following one: c to the a to the x minus 1, right? No, x to the a minus 1. X to the a minus 1 exponential of minus x. No, minus cx. Le ho cannate tutte. Okay, so we have c to the a to the, no, c to the a, x to the a minus 1, e to the minus cx. This over the gamma function of a. Okay, correct. So, again. The gamma distribution is given by c to the a, x to the a minus 1, exponential minus cx over gamma of a, where gamma of a is the following thing. It's the integral from 0 to infinity of let's just guess x to the a to the x minus 1 no, x to the a minus 1 was correct, exponential minus x dx. Now the thing I don't understand is why this is a function of a and we are integrated with respect to x. So let's try to repeat this again, because it's quite difficult, for me at least, to remember it. The gamma distribution is the following one: c to the a to the x minus 1, exponential minus cx over gamma of a, where gamma of a is the integral from 0 to infinity of x to the a minus 1, exponential minus x dx. Next is the Gaussian, famous Gaussian or normal distribution. And it's the distribution in differential form, which is basically the density. This is an important point. So And the thing I would like to do to understand better is how to interpret this. This in terms of notation and the idea behind it. Anyway, this is much easier. It's 1 over 2 pi p exponential of minus 1 over 2 x minus mu, let's call it a over b c dx. Let me see here if this is the same. Yes. And here we have the a is a real number. Many times I simply prefer just to say this and avoid writing it, because it's a waste of time to write it. I mean, I just slows down things. We have a is a real number and b is a positive number because it's a variance, and the variance is always positive by definition, by construction, because the variance is basically this thing here. Well, -1 if we want to correct it, if I remember well. I always forget formulas. Anyway, let's now get into spicy examples of distributions. And the first one is, well, you can see this as a continuation of the previous ones. Independent gamma random variables. So consider gamma. Well, I will just, okay, let's write it in this way. We have gamma A and gamma B, and I think they have the same scale factor equal to 1. Their joint distribution, which we call pi dx dy, because we have two variables. This thing factorizes, which means it turns into the product of gamma A of dx. I mean, it factorizes into the product of the marginal distributions, the y, which more explicitly should be something like a nightmare for me. So the first one should be c to the a to the x to the a minus 1, e to the minus cx over gamma of a, while this multiplies c of p. Well, in this case we don't have this because c is 1, y to the p minus 1, e to the minus, well, in this case we don't even have this, so e to the minus x, e to the minus y, gamma of p. E se ci ho preso, festeggiamo. That's correct. Nice. Let's go. So, okay. I think I will probably forget this formula and I should write it more times. But anyway, let's keep going. And now we have a crucial example, which will motivate what we will do from now on. So, this is the Gaussian with exponential variance. So how was it written? We have that the joint distribution is something like this: 1 over square root of 2 pi x exponential of minus 1/2 what can I put here? Well, here it's written simply like e to the minus y squared over x, right? Or 2x dx dy dx dy. And this is an important example because we have the variance. By exponential variance we mean variance which follows an exponential distribution. So the variance x is another random variable, so this joint distribution depends. So we simply cannot split the joint distribution into two marginals, because the distribution of y depends on the distribution of x. And here at this point, well, let's rewrite this in this way: dx dy. I don't know why the book prefers to put it in this way. 2x, okay, exponential minus y squared over 2x. And at this point we can see that we have two kind of elements. We have this one and this one. Ma che sto dicendo? I'm a buffo. I'm completely stupid. I forgot a crucial point. Forget everything I said. Let's consider this one instead. So it's dx dy c e to the minus x e to the minus cx. And now yes, 1 over square root of 2 pi x exponential minus y squared 2x. Now yes, we have this thing here, no, this thing here, and this thing here, which can be written in this way: mu dx, which is simply the marginal distribution of x. So this thing here we can just group and consider it as the distribution of x, and the other object depends on x also. And we will call it in this way: k of x dy. And we call it in this way with not just x and not dx, because we just integrate with respect to y, but it also depends on x. And this is not a product symbol, it's just x. Okay. So this is the integral with respect to y, but depends also on x. So now you can see when we have dependence, some kind of dependence structure for joint distributions, things become more complicated. But we still are interested, as I mentioned before, to the joint distribution of the process. And this is why we want to focus on this object right here, which will be called Rullo di Tamuri transition kernels or transition probabilities. And just to conclude this example, the marginal of y. So we derived the marginal of, this is the marginal of x, but if we want the marginal of y in this case, what is this thing? We consider the product, well, the distribution. I don't really how to read this. Of R plus Cartesian product with B, right? Yes. This, by definition, is the integral from 0 to infinity, should be. Since we have the exponential, or from minus infinity to infinity. From, I don't know, here we have this thing, so from, note, this is the same basically as integral from 0 to infinity. So the integral over R plus of all this thing right here, excluding the margin of x, if I am correct. So it should be 1 over square root of 2 pi x exponential minus y squared 2x dx. No, I was joking, the y. But before that, we should write it in this way: r plus of mu dx k of x dy no k of x and b but why do we write it in this way here? While here we had dy. What is this link here? Well, let's keep going. R plus, it's indifferent if it's above, below, it's the same. Here we have this dx dy. I mean, this is a bit confusing in the notes. It's not really linear, maybe, in the way it is written. It should be this before that, I think. R plus cross b dx dy, and this should be the entire density. Yes, this thing here, all this expression here, you put it here. And now this corresponds to the integral over b dy n of y, where n of y is the integral from 0 to infinity of all this thing here, right? Correct. This is a quite tricky section. It's actually probably the most difficult one that one faces at the beginning and in the middle and in the end, because I still find it quite difficult to understand. But at least we are trying to get familiar. And with this said, let's start defining transition kernels. Decays. Let's make a star. This is not maybe a nice star. Okay, no. Transition kernels. Let's give the definition of a transition kernel. So consider two measurable spaces E and F. I will just call them measurable spaces E and F when just to summarize and to be quicker. But remember that this is a measurable space with a set E and a sigma algebra on the set E, blah blah blah. So a transition, let's call a mapping a function K from the product sigma algebra to 0 infinity with 0 excluded. Now I'm thinking, what happens if we have transition kernel with infinity values? Anyway, a function like this is called transition kernel from E to F if from, well, transition kernel, let's write it from the space E to the space F to space F if two things happen. Or we can check through properties. Okay, no. Here I have it in this way. It's from E cross sigma algebra F to R extended, which is the same, but it includes also the 0 in this case, since it's R extended. Question. What happens when K explodes? Example. So, given two measurable spaces, a function K from E cross calligraphic F to R extended is called a transition kernel from the first space to the second if for X in E, K of X and B, the map which to X associate K of X and B is E measurable for any in here, and the map which to a set B associates k of x and b again, but I mean this time we fix b, here we fix x, and here we fix b. So we should use a not question. How to write with dot notation. If we fix x, I think we should have a dot here. If we fix b, I think we should have here a dot. So this thing is a measure on E or on F? On F. On F. On space F for any B. This thing is for any B, for any B in F. It's a measure on F for any X on E, correct? Measure, here it doesn't say this, but it should be a measure on F, I think. So the question is it a measure on F? Let's write it again. So K transition kernel from E script E to F script F. Well, let's write it this K from E cross sigma curly F to R extended transition kernel if the map in which we to X associates K of X and B, E mesh for B in F. This should be an F, and the map in which to B associates X of K of X and B mesh it's a measure for X in E. Now it should be a nice concrete example of this, and I still fall short in this on this side. I find it difficult to find a concrete example or a simple example of this. But here we have an abstract example, which is the following. So consider mu finite. Finite measure on the space. See, I don't know why you call it sigma F, but it's script F. So we have this and K, positive function across F, measurable with respect to the product sigma this is not very correct way to write it. This is a positive function. So it is measurable with respect to the sigma, the product signal algebra. Then this thing here, integral over b, right? No, it should be over, yes, over b of mu dy, k of, this is a little k of dx dy, no, of x m y. No, it's x dy. Question: how to interpret this formula? What is this thing here? I don't understand it. So we have a finite measure, and k is a positive function. No, it's defined here, but shouldn't it be like this thing? And here I don't understand this integral. Well, this thing here defines a transition kernel from E to F, from the space E to the space F. And this is for any B in F, and for any A in E, no, for any X in E. Okay, so this is the definition of a transition kernel, which is an hybrid object. If we fix points, it is a measurable function. If we fix sets, it becomes a measure. How is this possible? I still don't know. But the following is a theorem, an important theorem, which this is a good claim. The following theorem generalizes the law of total probabilities using transition kernels. General law of total probabilities using transition kernels. Anyway, so what does the theorem say? It says the following: K transition kernel from E to F. I will write it in this way. If we have this, then for any x in E, we have k of x, kf of x, capital K of x. I would capital Kf of x, which is the integral over E mu dx, k of, I was joking, this is f of y, k of x dy, correct. Yes. This defines a function kf which is immeasurable and positive for any f which is measurable with respect to the decimal algebra f. Now, I still find it difficult how to interpret this formula in a concrete example, but let's go to the second point. So for any set B in the sigma algebra F, we have mu k of B, the integral over B here, so this is a function. Now, I don't understand why this is a function, because we already have a function here, and this is used as a measure. This mu, forget. In any case, so here we have mu dx, k of x and b. And this thing defines a measure mu k on f, in space f, for any measure mu on space E. Now my question is, let's just mention it. How does this result generalize the law of total probabilities? Do I actually remember what is the law of total probabilities? No. But okay. Now for x in E, B in F, B in script F, we have that mu k of F is the same thing as mu of kf, and more explicitly the integral over E mu dx, integral over f, f of y, k of x and y, k of x dy. So these two things here coincide. Mu k question. How to interpret this formula? What is the difference between these two notations? I mean, the idea, the different idea between these two things, what is it? My PC is running low on battery. And this, well, this nothing, this ends the statement. So this is the first important result that I need to know, and is also asked in the oral exam. And I should actually try to prove it. I have some strange thing here in the notes, but in any case, this is for any measure on E, and F which is measurable and positive. Now a brief parenthesis about the notation. We write usually in this way, mu f to denote the integral of f, the function f, with respect to the measure mu, which means the integral over E, let's call it, yeah, over the entire space f of x mu dx, which we also write more concisely, so integral over E f d mu. For example, if we consider as function the indicator function on, let's call it p, we have that the integral of this function with the measure mu is the integral over E indicator of p. Well, this should be of x. Yes. Well, here it's not written, but the mu dx. But this thing here is the integral over b, because we restrict ourselves with the indicator function on this set, which is smaller than b, than the entire set of mu dx. Okay, and this is nothing but the measure of b. So if we, what is the implication here? The interpretation or meaning is that if we integrate an indicator function with measure, we get the measure of the set. Okay. Proof. Let's go with our first proof finally, and this will be a quick a long one for me. So first we have to prove this thing here. Let f be positive and measurable, because we have to prove it for any f, so fix it. Then kf is a positive and well-defined function on E. Why? Since the numbers kf of x well, the number, because it's just the evaluation on a given point, this thing is the integral of, so this defines a function, and by definition k is a transition kernel. Let's recall the definition so that we can understand this thing better. K transition, well, mapping k from E cross script f to R extended tk is a transition kernel if the mapping which to x associates k of x and b is a measurable E. No, this was for any set. For any B net. Measure. Define some measure for any X in here. So we start with the assumption that K is a transition kernel and okay, of F with respect to the measure which to B associates K of X and B. Now we show that Kf is measurable in 2 steps. If F is simple, meaning that it can be written as a linear combination of indicator functions, well, f of x can be written this way. Well, let's use the same notation. For any b I, well, then f of x is the sum bi k of x bi, and I don't know what this means. Why it is done in this way, I don't know. And this shows that Kf is immeasurable. Now, if F not simple, choose Fn increasing to F simple, such that Kf Kfn of x increases to K of Fn, K of F. Okay, this is as linear combination of immeasurable functions. x. Okay, f of x is the limit over n, k of n of x for any x by the monotone convergence theorem for the measure which to be associates k of x and b. Yes. So kf is immeasurable because it's the limit of immeasurable functions fn. Now we prove 2 and 3 together. We are at half of the proof. Now fix a measure mu on the space C. And define the function L from script f to our extended positive such that L of f is equal to mu of f, or no, mu of kf. My question here is, what does all these things mean? I don't understand the steps. So we define this function, I don't know why we define this function this way. Why here? What is the meaning here? Well, we have if f, and well, actually this proof relies on another theorem that we will see maybe next. Yeah. Okay. So if f is 0, we have that L of f is 0. I don't know why. And now if f and g are measurable positive measurable functions with a and b real numbers, then L of AF plus BG more explicitly is mu of K of AF plus BG, and by continuity of the measure K xb, this can be written as mu of KAF plus KBG, and again by continuity of the measure mu, well, sequential continuity is justified by linearity. The continuity has nothing to do here. It's the linearity of the integral with respect to a measure. But in any case, mu KAF A mu KF plus B mu KG, and this is nothing but AL of F plus BL of G. And I don't know what is the role of this step. Question. what is the role of this step in the proof? Finally, if we have a sequence of positive measurable functions increasing to f, then k fn of x increases to k of f of x by the monotone convergence theorem of the measure, which B associates k of x and b, and L of n is k of, it's mu k, right? Mu of k of n, and this thing increases to mu of kf, which is L of f. By MCT of mu. Now, I don't remember actually what the monotone convergence theorem says. I remember maybe that if we have an increasing sequence of functions, then the measure, the integral of the limit is equal to the limit of the integral is equal to the integral of the limit, which is basically equivalent to this. Okay. Okay. Hence, by theorem, which is this one, I will simply write it a plus 2r extended, then there exists a unique measure mu on space E such that L of f is mu f. What is this thing? I don't know. And yeah. Here it's immeasurable apparently. And this is if this happens if and only if f of 0 is equal to 0. No, f is equal to 0, then L of f is 0, and given a and b real numbers, we have that this thing here is the linear combination of, I don't know what this is, of this thing. And given a sequence of functions with f n increasing to f, Now this is written a bit strangely here, but L of Fn increases to L of F. So now, by this theorem, we can say this is a theorem that characterizes integral with respect to a measure. Hence, there exists a unique measure nu on F, on space F, such that L of F L of F is equal to nu F. So this is what the theorem implies for any F. And now the thing that is not completely clear to me is why this and why this, which are different. Now taking as a function the indicator function B, we see that nu of B, nu of B is mu k of B. For any B in F. Which means mu is equal to mu k. Yes. And this concludes the proof. So what did we do here? We find the transition kernels to construct probability measures on product spaces. And this theorem explains how transition kernels can do something which is quite obscure to me yet. It can be used as a function or as a measure, and in either case we get the same. What is this thing which I call same? I don't know. And to prove this theorem, we use some tricks which are not impossible to remember, but a bit difficult to understand sometimes. Okay, so in the first case, we show that kf defines a function which is positive and measurable for any function f, which is what we do here. And we do that by considering, simple functions, not simple functions, blah blah blah, and exploiting the fact that the kernel is a measure. So we can use the monotone convergence theorem. And here we prove that this defines a measure using this theorem, which characterizes the integral with respect to measures. So we use this theorem here, and the last part, which is this one, the third point. I don't know how we prove it. Well, taking this thing and just making an observation, I think. So let's find a question. How did we actually prove 2 and 3 together? Well, I think this is enough for now. I don't know if I will keep doing probability theory for today. Maybe I will just read and consolidate some proof writing. And just to let you know, this is basically page 1. We finished page 1, and there is a total of 10 pages in my notes. So what did we see today? We started talking about the properties of a probability measure. We gave the definition of a distribution of a random variable, distribution of a random variable, joint and marginal distributions. Then we talked about the independence of 2 random variables and random variables and an infinite number of random variables. Okay, so we started talking about the construction of infinite product spaces and how to create measures on those product spaces by the use of kernels. That's it. Well, I hope you found it at least interesting, and if you arrived at this point and could bear all the tedious explanation, which was quite bad, but then anyway, see you next time.